Welcome to episode 2 in our series on how we can use simulation for industrial electrical equipment. In this episode, we're going to be using Autodesk Simulation Mechanical 360 to see how vibrations affect your equipment. My name is James Herzing. As a quick review of episode 1, we saw that Autodesk Simulation provides solutions through mechanical, CFD, and mold flow for your simulation needs, but is now innovating the way simulation is done with its Simulation 360 products. The episodes we're going to be looking at are how vibrations affect your equipment, thermal and CFD testing, and drop testing your equipment. After you go through these, you should be able to reproduce these exercises on any of your own models very quickly and without much trouble. We're going to actually be using an electronic drive system enclosure throughout this whole process to show you how you can use your same CAD model through all of these analysis types. You're actually able to get this model and practice on it through a website at the end of this presentation. So there's some advanced engineering and manufacturing simulation solutions that we're offering. In particular, in this episode, Simulation Mechanical 360. This is where we're going to be using statics, dynamics, structural analysis, all to see if our part's going to be damaged due to vibrations in this situation. You can also look at Simulation 360 for CFD and use our DFM and mold flow solutions for injection molding. So what are the reasons for concern about vibration? Well, an increase in vibration can cause an accelerated rate of wear in components, meaning you're going to have to replace them sooner. Vibrations also cause noise, leading to safety problems in the factory, or at least a degradation in the working environment. Vibrations also cause equipment to consume excessive power. The power alone is expensive, but consuming it could cause damage to the equipment and knock a line out completely. Some common causes for vibrations in equipment would be imbalances or uneven weight in the machinery, misalignment of machines if the shafts are out of alignment, wearing of belts or other components, and as in the example we're going to be looking at, just the running of motors and fans. A fan similar to this one is being used in our example today. So why use simulation over traditional testing? Well, there are a number of reasons, some of which would be material selection for damping. You don't have to create a prototype of different material types. You can just go through the library, choose the materials you think would be suitable, and see which ones might damp out the vibrations the best. Part thickness can be analyzed, so determining the thickness of mounting plates can again reduce the vibrations in your models. All of these different variations can be run in multiple design scenarios in parallel on the cloud, saving you time and money. And again, this is all being done to avoid expensive testing, which is time-consuming and makes you have to have many prototypes to do these different analyses. So let's go ahead and get into the software to see how we go through this random vibration analysis with Simulation Mechanical 360. We're going to start out here in Inventor. If you aren't an Inventor user, you can easily use the Fusion software that's provided with the 360 download. Why are we here? Well, this is the first thing that I really want you to pay attention to for not only this model, but for when you're working on your own models. And that's to simplify your geometry. We have all these wires that I'm highlighting right now that I'm going to suppress. These are going to just lead to a higher element count when I mesh my model, and they're not really going to affect the results of the model very much. They're very small, they won't weigh much during the vibration. They really aren't necessary for this analysis. Getting rid of unnecessary detail can save you a lot of time and give you better results. So now that we have the model saved, we're going to launch Simulation Mechanical 360, and as you're going to see, the model is going to transfer over to the product on our desktop where we're going to be able to mesh and load it and then analyze it in the cloud. So as the part comes over, we're going to have to decide what type of analysis do we want to run. We're going to choose a modal analysis because before we can run a random vibration analysis, we need to determine what natural frequencies we're going to be concerned with. So as you can see, we have a number of parts in our model tree. The first thing we're going to have to do is mesh all of these parts. There are actually two types of parts that we're working with here though. You may have noticed in Inventor there were a number of surface parts. All of those surfaces are going to be defined to use a plate shell mesh. So we're going to go ahead and mesh those with an absolute mesh size of 0.5 and click OK. And then again, we're going to select the rest of the plates. You can see that they look a little bit different in the model tree, indicating those are surfaces. We're going to select those and again apply the part mesh settings, defining those to use the plate mesh. So we click on part, the radio button next to plate/shell, and again we'll define the absolute mesh size of 0.5 and click OK. The rest of the parts in the model tree are bricks. So we're just going to click on the Mesh tab and click on 3D Mesh Settings. And again, in these options, we'll set the mesh to an absolute value of 0.5, and we should have a nice consistent mesh through all of our parts where everything matches up and works nicely. You can play with these values to see what works best for you and can optimize the runtime. After finishing with the mesh, we can go ahead and select all of our parts that are of the same type. So all of them that are bricks or plates you can define at the same time. In this case, we're going to define our bricks and edit the materials. Here we can make our material, let's say, I don't know, aluminum for the outside and the inside components of our enclosure. And click OK. And now we can choose to select all of our parts, or all of our plate parts. When we do that, we're going to start by defining the element definition and giving them a thickness. So we're going to say that the thickness of these walls is 1/4 of an inch. Now I realize that's pretty thick, but for this analysis, that's one of the beauty of running on the cloud. You can just run as many scenarios as you want. You can run 1/4 inch, 1/8 inch, 1/16 of an inch. All of these can be run in parallel on the cloud. So you can see that that has now been defined. We're going to just skip ahead and have finished defining the materials for all of these parts. And now we can define some boundary conditions. We're going to just flip the parts over and grab the bottoms there and choose General Constraint and choose Fixed. So we're acting as though these are tied down to the floor somehow. And now we can choose to analyze the model. We can press Analyze, and the model will be sent to the cloud where it will give you your results, and then it will be sent back to you. You can see here, our parts have finished analyzing. We can determine the different frequencies. We requested 5 modes, so we're checking out the first 5 frequencies ranging from 23 to roughly 55 cycles per second. With that, we're going to go back to the FEA editor and see how this will react with the running of the fan. Are we going to see high stress or not? So to the FEA editor, we're going to change our analysis type from natural frequency modal to random vibration. And again, this is being done on your desktop, but all of the solving and all of these different analysis types can be run in the cloud. So all we have to do here, since the model is already set up, is go to the analysis parameters and point to the design scenario that we ran everything in, and browse to our file, .csv. So what is this? This is our curve that we're inputting. So if you have this data, if you're running a fan or something of that sort, you probably have this data handy. We click OK, and this is going to be all we need to do before we press Analyze. Again, Analyze, this goes off to the cloud. Your computer is free to do anything you want. When it's done, it comes back, and you notice that for each load case or each natural frequency, it's determining what the stress is going to be. You see, for the first one, it's negligible. For the second, 63, still very small. Again, you would hope that this fan wouldn't be causing a lot of stress in these models, but you can see that some of it is being a little higher stress because of the movement of the fan. Still, nothing of any great damage, so we're not too concerned. All right, so now that you've seen how this is done, why don't you go ahead and download the model at the link above. Type that in, grab the model, and then just follow the steps that I did to see how this works for you. You're going to be able to apply the same steps to your own models and easily be able to come up with the solutions with simulation for your own problem soon. The 3 things you're going to have to focus on for this model and for your own would be 1, simplifying your CAD geometry, meaning getting rid of details that you don't need and eliminating parts that aren't necessary for the analysis. 2, define the meshing conditions. A nice mesh is what gives you good results. And 3, input your loads and review these results. An accurate loading condition will result in accurate results for you to look at. If you have any trouble with getting these files, questions on this video, or trouble with installing your software, please feel free to reach out to me at simsquad@autodesk.com. Also, you could call me at 855-237-5746, and I'd be happy to walk you through anything that you need help with. If you want to go off on your own and learn a little bit more about the simulation solutions that we have, you can go to Simulation-TV, where you can see more videos such as this one offering help on any number of simulation problems, as well as giving you tips and tricks about how to use the software. Thank you for viewing, and I hope to see you for next episode.